Here's an old postcard picture of San Francisco's Golden Gate Bridge. Let's say you're standing on the road deck of the Golden Gate Bridge and you drop a heavy rock. How far does the rock fall in 3.0 seconds? Now, the first thing to do in this problem is to parse the words, to decipher exactly what information we know based on the words. Let's start with a heavy rock. The implication here is that air resistance is not important. So we can assume that the rock is going to fall with an acceleration equal to little g of 9.8 meters per second, or 9.8 meters per second squared. What's being asked for is how far does it fall? It's asking for the distance, or delta x. So I'm going to write delta x equals question mark. And we're given a time interval, a delta t, of 3.0 seconds. So all that information is given in the problem, and now we can go ahead and do our calculation. Delta x is equal to v naught delta t plus 1/2 a delta t squared. Now there's one other piece of information that I forgot to mention in parsing the given problem, was this word drop. What is implied there is that the initial velocity was 0. If the rock was moving, you'd say you would throw the rock. But if you're just dropping it, that means it has no initial velocity. The acceleration is little g, so I'm going to write 1/2 gt squared equals 1/2 times 9.8 meters per second squared times 3.0 seconds squared. So we have 4.9 meters per second squared times 9.0 seconds squared. Cancel out our units. That gives us 44.1 meters. Now, because we were given two significant digits in the original statement of the problem, we would round that to 2 sig figs, 44 meters. Now, an interesting follow-up to this question is, when the rock has fallen 3 seconds, how fast is it moving at that moment? For this, we're going to use our equation that defines what we mean by the word acceleration. A is delta v over delta t. That, with a little algebra, gives us delta v is equal to a times delta t. Now, what does delta v mean? Delta v means v minus v naught, the velocity at the moment we're interested in, minus the initial velocity. What we really have here then is v equals v naught plus a times delta t. The velocity is equal to the initial velocity plus the change in the velocity. Our initial velocity, however, was 0. Our acceleration is negative 9.8 meters per second squared, and our time was 3.0 seconds. This gives our velocity as negative 29.4 meters per second. Units seconds here cancels the square of the seconds on the bottom. And because we only have two significant figures, that's negative 29 meters per second. The rock is moving 29 meters per second in the downward direction.